Hello everyone! Welcome to this informative video on the fascinating topic of surface tension in our lungs. What is surface tension? Water molecules form an intermolecular force between each other called cohesion. As the water molecules on the surface have no other water molecules on the above to interact with, cohesion force between that molecules and water molecules beside and below will be stronger, creating the surface tension of the water to resist an external force.
And actually, we also have a surface tension in our body, in our lung. Inside the lung, there is a functional unit called alveoli, where it has an alveolar fluid layer with a surfactant coated on the alveolar fluid surface. Alveolar water molecules attract to each other to form a liquid sphere. Then it creates surface tension to the layer, causing the alveoli to change its shape. Type 2 alveolar cells secrete surfactant composed of lipid and protein, forming lining fluid, where it has an important role in reducing surface tension inside the alveoli by weakening the water bond in alveolar fluid layer.
Now that we have understood the concept of surface tension within the lungs, let's turn our attention to how disruptions in this delicate balance can lead to the onset of critical condition known as respiratory distress syndrome or RDS. In premature infants, especially those born before their lungs have had a chance to fully develop and produce sufficient surfactant, there is a risk of insufficient surfactant production. This results in increased surface tension within the alveoli, making it difficult for infants to breathe effectively, leading to RDS. Newborns with RDS often require medical intervention and respiratory support, such as mechanical ventilation or surfactant replacement therapy, to help them breathe until their lungs mature and produce enough surfactant on their own. We will demonstrate the experiment related to surface tension in lungs by using coin, water, and oil. Experiment 1. Normal surface tension. When a water droplet lands on a coin, it tends to pull together in the center, creating a thicker layer of water. This happens because water molecules have cohesive forces that make them stick together, causing the droplet to form a rounded shape with a thicker center. Normal surface tension, water molecules tend to form the intermolecular force between each other. Create surface tension cause the alveoli to collapse. Experiment 2. Decrease surface tension by surfactants. When we add an oil to water molecules, the water drop is thinner due to surfactant increases. The water molecule on the surface can interact with the polar hydrophilic head of surfactant. Water now can move more freely than before, and this causes the water layer below the surface expands, resulting in the intermolecular bond between the water breaks. When this occurs in the fluid layer of the alveoli will inflate. Let's compare between normal surface tension versus decreased surface tension by surfactant. As you can see, as we add the drop of oil, the layer of the water droplet will become thinner because the oil reduces the surface tension, while the layer of water droplet on the coin with only water is thicker.
According to the Laplace law of spheres, pressure equal to times surface tension divided by radius. The units of pressure would be expressed in Pascal. The unit of surface tension is the Newton per meter, and the unit of radius of length is meter.
Why do we have to use the Laplace law in this topic? Laplace law is used to explain how surface tension in the presence of surfactant maintains the structural stability of the alveoli. Laplace law can be used to state that the pressure inside the alveoli is directly proportional to the surface tension and inversely proportional to the radius, where it's used to explain how surface tension affects the stability and behavior of alveoli. This means that the smaller alveoli would tend to collapse due to their higher internal pressure than the larger ones. However, the presence of surfactants in alveoli helps to reduce surface tension and lower the pressure, preventing them from collapsing. and is used for calculating the stability of alveoli, which is crucial for efficient gas exchange. Understanding Laplace law and the role of surfactant is important in managing and treating RDS, often by providing artificial surfactants to improve lung function.
Let's recap for a bit. In the normal state, water molecules tend to form the intermolecular force between each other, create surface tension, increases the collapsing pressure in the alveoli, and cause alveoli to collapse. But when we increase the surfactant, the hydrophilic head of alveolar fluid will turn over to water molecules and make the interaction cause the water layer below the surface expands, resulting in the intermolecular bond between the water breaks. Having an increase in surfactant will decrease surface tension on the alveolar fluid layer and decrease in collapsing pressure, causing the alveoli to inflate.
And this is information resource of our videos. Hope you would get some concept of surface tension in lungs. Thanks for being with us through the whole videos.